Temperature is one of the important variables in any industrial process. Le Chatelier's principle can be used to predict the effect of temperature on the equilibrium of a reaction. You have learned that whenever a system at equilibrium is subjected to change in concentration or pressure, the reaction quotient QC no longer remains equal to the equilibrium constant Kc. However, when a system at equilibrium is subjected to change in temperature, the value of equilibrium constant Kc itself changes. For example, the equilibrium constant for the gas phase reaction of the formation of ammonia from nitrogen and hydrogen at 298 Kelvin is 6.8 multiplied by 10 to the power of 5, while it is 41 at a temperature of 400 Kelvin. The value of the equilibrium constant for a given reaction varies with temperature. In general, equilibria in which the forward reaction is exothermic, that is, where the enthalpy change is negative, have equilibrium constants that decrease with an increase in temperature. For example, the gas phase reduction of nitrogen and hydrogen combining to give ammonia. In this reaction, the forward reaction, that is, the formation of ammonia, is an exothermic reaction, and the backward reaction of ammonia dissociating into nitrogen and hydrogen is an endothermic reaction. According to Le Chatelier's principle, raising the temperature shifts the equilibrium in the direction in which the heat is absorbed. It implies that endothermic reaction is favored. So, ammonia absorbs the heat to dissociate into nitrogen and hydrogen. Hence, on increasing the temperature, the rate of backward reaction increases, or the rate constant for backward reaction, Kb, increases. You have also seen that equilibrium constant Kc is equal to Kf divided by Kb, where Kf and Kb are rate constants for forward and backward reactions respectively. As Kb increases in the denominator, the value of Kc decreases. Thus, for an exothermic reaction, the value of the equilibrium constant decreases with an increase in temperature. Equilibria in which the forward reaction is endothermic, that is, where the enthalpy change is positive, have equilibrium constants that increase with an increase in temperature. Consider the gas phase reaction of the decomposition of phosphorus pentachloride into phosphorus trichloride and chlorine. The positive enthalpy change for this reaction indicates the endothermic nature of the forward reaction. If the temperature for this reaction is raised, then the forward reaction of PCl5 dissociating into PCl3 and Cl2 occurs. As the rate of forward reaction increases, the rate constant for the forward reaction, Kf, and consequently, the value of equilibrium constant Kc also increases. Thus, for an endothermic reaction, with an increase in temperature, the value of equilibrium constant Kc also increases. The effect of temperature on equilibrium can be demonstrated using nitrogen dioxide gas. Nitrogen dioxide gas, which is brown in color, dimerizes into colorless dinitrogen tetraoxide. This dimerization as you can see from the value of delta H, is exothermic in nature. The three identical sealed tubes that you see here contain nitrogen dioxide in equilibrium with dinitrogen tetraoxide. As you can see, all the three tubes contain the same amounts of NO2 and N2O4 and have the same brown appearance. Now, out of the three sealed tubes, one is placed in a freezing mixture, one in hot water, and one is left at room temperature. What do you observe? You can see that the tube placed in a freezing mixture has turned pale, while the one placed in hot water has turned dark brown. How do you explain this? The forward reaction of NO2 dimerizing into N2O4 is an exothermic reaction. You have seen that increasing the temperature for an exothermic reaction favors the backward reaction. Hence, the backward reaction of formation of NO2 occurs when the tube is placed in hot water. This is why you see that the brown color intensified in that tube. Lowering the temperature for an exothermic reaction favors the forward reaction. Hence, when the tube is placed in a freezing mixture, the forward reaction of NO2 dimerizing into N2O4 is favored. That is the reason why you see the tube turning pale. Now, let us look at the influence of a catalyst on equilibrium. A catalyst has no effect either on the position of equilibrium or on the equilibrium composition of a reaction mixture. However, a catalyst increases the rate of the reaction by providing a new low-energy pathway for the conversion of the reactants into products. A catalyst lowers the activation energy for the forward as well as the reverse reaction by exactly the same amount, and thus makes it easy for the reaction to proceed faster in either direction. To understand the effect of a catalyst, consider the gas phase reaction of the formation of ammonia from hydrogen and nitrogen. The formation of ammonia is an exothermic reaction and proceeds with a decrease in the number of moles. According to Le Chatelier's principle, the conditions favorable for the formation of ammonia are low temperature. Since the forward reaction is exothermic, and high pressure, as the reaction proceeds with a decrease in the number of moles. However, the conditions cannot be maintained because at low temperature, the reaction is so slow that it makes the process uneconomical. High pressure gives a high yield of ammonia, but the higher the pressure, the greater is the cost and maintenance of the equipment. Fritz Haber, a German chemist, discovered that using a catalyst consisting of iron permits lower operating temperatures and a moderate pressure. Thus, the optimum conditions for the industrial method of the synthesis of ammonia by Haber's process are a pressure of 200 atmospheres, a temperature of 725 to 775 Kelvin, and an iron catalyst to speed up the reaction. The importance of a catalyst can also be understood by its use in the manufacture of sulfuric acid by the contact process. One of the important steps in the manufacture of sulfuric acid by the contact process is the formation of sulfur trioxide from sulfur dioxide and oxygen. The forward reaction leading to the formation of sulfur trioxide is an exothermic reaction, involving a decrease in the number of moles. Thus, according to Le Chatelier's principle, low temperature and high pressure favors the formation of sulfur trioxide. However, at low temperature, the reaction is very slow, while at high pressure, the tars used in the synthesis get corroded. Hence, to maintain optimum conditions and increase the rate of the reaction, a catalyst such as platinum or vanadium pentoxide is used. The optimum conditions used for the industrial synthesis of sulfur trioxide are normal pressure, a temperature of 673 Kelvin, and a catalyst such as platinum or vanadium pentoxide. In this image, one beaker contains aqueous sodium chloride solution and the other contains aqueous sugar solution. How will you identify which beaker contains the salt solution and which contains the sugar solution? Obviously, the beaker indicated by the glowing bulb contains the salt solution, and the other beaker, where the bulb is not glowing, contains the sugar solution. Substances like sodium chloride, which conduct electricity in their aqueous solutions, are called electrolytes, and molecular compounds like sugar, which do not conduct electricity, are known as non-electrolytes. This classification of substances into electrolytes and non-electrolytes based on their ability to conduct electricity was made by the English chemist and physicist Michael Faraday. Michael Faraday further classified electrolytes into strong and weak electrolytes. According to him, strong electrolytes undergo dissociation completely when dissolved in water, while weak electrolytes undergo dissociation only to a limited extent. For example, HCl is considered a strong electrolyte as it undergoes dissociation completely when dissolved in water. An aqueous solution of HCl contains only H+ and Cl- ions. On the other hand, acetic acid is considered a weak electrolyte as it undergoes ionization to a very limited extent. An aqueous solution of acetic acid mainly contains unionized acetic acid molecules in equilibrium with the few hydrogen and acetate ions. Hence, the equilibrium involving the ions in an aqueous solution of a weak electrolyte is called ionic equilibrium. Ionic equilibrium can be conveniently studied under two headings: dissociation equilibria, solubility equilibria. Dissociation equilibria. The equilibrium between a dissolved undissociated molecule and its ions is known as dissociation equilibria. In general, dissociation equilibria involve either acids or bases. We deal with many acids, bases and salts in our daily lives. Even some food items contain acids. For example, orange juice and lemon juice contain citric and ascorbic acids. Tamarind paste contains tartaric acid. Curd contains lactic acid. Spinach contains oxalic acid. Salads which are flavored with vinegar contain dilute acetic acid. Isn't it amazing that HCl is produced in our body and helps in digestion? The bases commonly used in our daily life include ammonium hydroxide in cleaning liquids, magnesium hydroxide as an antacid, and sodium hydroxide in the manufacture of soap. Many compounds known to us may be classified as salts. The salt most familiar to all of us is sodium chloride, which forms an important component of our diet. Washing soda used for washing and baking soda, which is used in baking, are also the examples of commonly used salts. The word acid is derived from the Latin word acidus, which means sour. Acids exhibit certain properties in their aqueous solutions. They are sour to taste. They turn blue litmus red. They react with active metals like zinc and liberate hydrogen gas. On the other hand, bases display the following properties in their aqueous solutions. They are bitter in taste. They turn red litmus blue. They are soapy to touch. Arrhenius gave the first real classification of the chemical nature of acids and bases, which is popularly known as Arrhenius theory. According to his theory, an acid is a substance that contains hydrogen and ionizes in an aqueous solution to give hydrogen ions. For example, HCl contains hydrogen and ionizes in water to H+ and Cl- ions. The ionization of hydrochloric acid in an aqueous solution can be represented in the form of equation 1 or equation 2 as shown here. As a bare proton, H+ is very reactive and cannot exist independently in an aqueous solution. Instead, it bonds to an oxygen atom of the water molecule and forms H3O plus the hydronium ion. A base is a substance that contains the hydroxyl group and ionizes in an aqueous solution to give hydroxide ions. For example, NaOH contains a hydroxyl group and ionizes in water to Na+ and OH- ions. The ionization of sodium hydroxide in an aqueous solution may be represented in the form of an equation as shown here. A hydroxyl ion, like H+, also exists in the hydrated form, like H3O2-. Although H+ and OH- exist in the hydrated form, for the sake of simplicity, we usually write H+ and OH- rather than H3O+ and H3O2-. However, the Arrhenius theory of acids and bases has some limitations. It is limited to aqueous solutions only. For example, HCl is considered as an acid only when it is dissolved in water and not in some other solvent such as benzene. Some substances exhibit the properties of a base, though they do not contain hydroxide ions. For example, liquid ammonia behaves as a base, although it does not contain any hydroxyl group in it. In an attempt to overcome the limitations of the Arrhenius theory, Danish chemist J.N. Bronsted and English chemist T.M. Lowry proposed a more general definition of acids and bases. According to the Bronsted-Lowry theory, an acid is a substance that exhibits a tendency to donate a proton, and a base is a substance that exhibits a tendency to gain a proton. In other words, proton donors are acids and proton acceptors are bases. Consider a generic acid-base reaction. HA plus water in equilibrium with H3O plus and A minus ions. In the forward reaction, HA donates proton to water and thus acts as a Bronsted-Lowry acid, while water accepts the proton and acts as a Bronsted-Lowry base. Did you notice that water, which acts as a Bronsted-Lowry base, has turned into a Bronsted-Lowry acid after accepting the proton, and the species HA, which acts as a Bronsted-Lowry acid, has turned into a Bronsted-Lowry base after donating the proton? This is because a Bronsted-Lowry base, after accepting a proton, becomes a Bronsted-Lowry acid as it has a proton to donate, and a Bronsted-Lowry acid, after donating a proton, becomes a Bronsted-Lowry base as it now has room to accept a proton. The species that remains after an acid gives up its proton is called the conjugate base of that acid. Similarly, when a base accepts a proton, the resulting species is called the conjugate acid of that base. Thus, such a related pair of an acid and a base, which differ by a single proton, is called a conjugate acid-base pair. In the generic example that we saw just now, H3O plus is the conjugate acid of the base, H2O, and A minus is the conjugate base of the acid, HA. Now, in the ionization of HCl in water, HCl acts as a proton donor and water acts as a proton acceptor. Hence, HCl and water are called Bronsted-Lowry acid and base, respectively. As you can see, in the reverse reaction, the H3O plus ion acts as a proton donor and the chloride ion acts as a proton acceptor. Thus, the H3O plus and Cl minus ions act as Bronsted-Lowry acid and base, respectively. Observe that the H3O plus ion, H2O, and the HCl and Cl minus ions differ from each other by a proton only. Therefore, you can say that H3O plus is the conjugate acid of the base H2O, and Cl minus is the conjugate base of the acid HCl. In the dissolution of ammonia in water, the water molecule acts as a proton donor and the ammonia molecule acts as a proton acceptor. Thus, the water and ammonia molecules are called Bronsted-Lowry acid and base, respectively. In the reverse reaction, the ammonium ion NH4 plus donates a proton to the hydroxide ion OH minus. Hence, NH4 plus and OH minus act as Bronsted-Lowry acid and base, respectively. In this case, the OH minus ion is called the conjugate base of the acid, H2O, and the NH4 plus ion is called the conjugate acid of the base, NH3. However, even this theory had its limitations. The theory fails to explain some reactions that do not involve a proton transfer. For example, the neutralization reaction between the acidic oxide, carbon dioxide, and the basic oxide, calcium oxide, does not involve any transfer of proton. It fails to explain acidic behavior of electron-deficient molecules like AlCl3 and BCl3. In 1929, G.N. Lewis proposed a more general theory of acids and bases, which is founded upon the electronic theory of valency. According to this theory, an acid is any molecule or ion that can accept an electron pair to form a coordinate covalent bond with the donor. For example, H+, BF3, AlCl3 and SnCl4 act as Lewis acids. A base is any molecule or ion that can donate a pair of electrons to form a coordinate covalent bond with the acceptor. For example, NH3, H2O and OH- ion act as Lewis bases. In short, an electron pair donor is a base and an electron pair acceptor is an acid. According to this theory, a neutralization reaction is simply the formation of a coordinate covalent bond between an acid and a base. For example, in the formation of NH3BF3 abduct, the boron of BF3 accepts a lone pair of electrons from the nitrogen of ammonia and forms a coordinate covalent bond. The Lewis theory had its limitations too. This theory fails to explain the strength of acids and bases. All the acid-base reactions do not involve coordinate covalent bond formation. For example, the reaction of HCl with NaOH does not involve any formation of a coordinate covalent bond. Generally, acid-base reactions are very fast, but in certain cases, the formation of a coordinate covalent bond is very slow. Of the two beakers, A and B, one contains hydrochloric acid and the other contains acetic acid. Identify which one contains hydrochloric acid. Beaker A, doesn't it? How do you explain that? Its brightly glowing bulb indicates the ability of the solution to conduct electricity, which, in turn, indicates the presence of a large number of current-carrying particles in the solution. HCl, being a strong electrolyte, undergoes almost 100% dissociation in water. As a result, the solution contains a large number of ions that help conduct electricity to a greater extent. Acetic acid, on the other hand, is a weak electrolyte and undergoes very little ionization. Thus, the solution contains mostly unionized acetic acid molecules. Therefore, very few ions are available to conduct electricity, and so the flow of electric current is weak. Hence, the bulb glows very faintly. According to the Arrhenius theory, the strength of an acid and a base is related to the ease with which they function as a source of H+ ions and OH- ions in an aqueous medium. As hydrochloric acid, sulfuric acid, nitric acid and perchloric acid undergo almost 100% dissociation, they are said to be strong acids. These acids act as proton donors. Similarly, bases such as sodium hydroxide, potassium hydroxide and cesium hydroxide are also called strong bases as they undergo complete dissociation in an aqueous medium, furnishing OH- ions. In terms of the Bronsted-Lowry theory, a strong acid is one that readily donates the proton, while a strong base is one that readily accepts a proton. The greater the tendency of an acid to donate protons, the stronger it is. Similarly, the higher the tendency of a base to accept protons, the stronger it is. To understand the statement better, consider the ionization of HCl in water. You can see from the equation that Cl- is the conjugate base of HCl and H3O+ is the conjugate acid of the base H2O. Now, as you can see, there are two acids, HCl and H3O+ in the reaction. Now, which one is stronger? Obviously, HCl. This is because HCl shows a greater tendency to lose protons than the H3O+ ion, and hence, the solution primarily contains Cl- and H3O+ ions. Generally, the equilibrium will shift in the direction of weaker acid, and the resultant solution mainly contains Cl- and H3O+ ions. As HCl is a strong acid, it readily loses the proton. Does this tell you anything about the chloride ion as a base? Yes, it does. HCl is a strong acid, which means that every HCl molecule produces H+ and Cl- ions. This further means that the forward reaction predominates in this reaction. In an aqueous solution, there are virtually no HCl molecules, but only H+ and Cl- ions. This shows that the Cl- ion has very little ability to attract the H+ ions in the water, and thus is a very poor base compared to the water molecule. Hence, it follows that a strong acid has a weak conjugate base. Strong acids like hydrochloric acid HCl, sulfuric acid H2SO4, nitric acid HNO3 and perchloric acid HClO4 have a very weak conjugate base like chloride ion Cl- ion, bisulfate ion HSO4- ion, nitrate ion NO3- ion and perchlorate ion ClO4- ion. Now, let's consider the dissociation of acetic acid in water. It is a weak acid. The term weak acid means that it undergoes dissociation to a less extent, and thus, very few ions are present in the solution. This means that the backward reaction predominates in its aqueous solution, and acetic acid remains largely in the undissociated form. This clearly indicates that the acetate ion strongly attracts the protons in the water, and thus it is a strong base compared to the water molecule. Hence, you can infer that a weak acid has a strong conjugate base. Weak acids like acetic acid CH3COOH and hydrofluoric acid HF have very strong conjugate bases like acetate ion CH3COO- ion, fluoride ion F- ion respectively. You might have observed that during acid-base titration reactions, indicators like phenolphthalein and bromothymol blue are used. Generally, indicators are weak organic compounds that exhibit different colors in acidic and basic media. For example, phenolphthalein is colorless in an acidic medium and pink in a basic medium. This change in color helps us in identifying the end product of an acid-base reaction. Observe the two reactions of the dissolution of ammonia in water and the ionization of HCl in water. What do you infer? You can see that water is capable of acting both as an acid as well as a base. Pure water is a poor conductor of electricity. Conductivity measurements show that water ionizes to a very limited extent. This equilibrium constant Kc for this equilibrium can be written as Kc is equal to the product of concentration of H plus ions and concentration of OH minus ions divided by concentration of H2O. Since the ionization of water is negligible, the concentration of water can be taken as constant. Thus, the concentration of H2O can be incorporated in the value of Kc to give a new constant, Kw, called the ionic product of water. The ionic product of water, Kw, at a given temperature, is defined as the product of the concentrations of the H plus and OH minus ions in water or in aqueous solutions. Experimentally, the concentration of H plus ions at a temperature of 298 Kelvin was found to be 1.0 multiplied by 10 to the power of minus 7 moles per liter. The dissociation of water produces equal number of H plus and OH minus ions, and hence the concentration of OH minus would also be equal to 1.0 multiplied by 10 to the power of minus 7 moles per liter. Thus, at 298 Kelvin, the ionic product of water, which is equal to the product of the concentrations of H plus and OH minus ions, is equal to 1 multiplied by 10 to the power of minus 7 raised to the power of 2 moles per liter. This is equal to 1 multiplied by 10 to the power of minus 14. Hence, the value of the ionic product of water at 298 Kelvin is equal to 1 multiplied by 10 to the power of minus 14 moles square per liter square. It must be remembered that Kw, being the equilibrium constant, depends on temperature. The aqueous solutions of various substances can be divided into neutral, acidic or basic, depending upon the relative amount of H plus and OH minus ions. In neutral solutions, the concentration of H plus ions is equal to the concentration of OH minus ions. In acidic solutions, the concentration of H plus ions is greater than the concentration of OH minus ions. While in basic solutions, the concentration of H plus ions is less than OH minus ions. The concentration of hydrogen ions is commonly expressed in terms of the pH scale, which was introduced by S.P.L. Sorensen. The P in pH comes from the German word Potenz, meaning power, and the H from the concentration of H plus ions. The pH of a solution is defined as negative logarithm to the base 10 of the molar hydrogen ion concentration in a solution. Thus, the pH of a solution containing hydrogen ion concentration of 10 to the power of -4 molar will be equal to 4. You have seen that at 298 Kelvin, the concentration of hydrogen ions in pure water is equal to 10 to the power of -7 moles per liter. Thus, the pH of pure water is 7. Thus, for neutral solutions, the H plus ion concentration is equal to the OH minus ion concentration, and the pH is equal to 7. For acidic solutions, the H plus ion concentration is greater than the OH minus ion concentration, and the pH is less than 7. For basic solutions, the H plus ion concentration is less than the OH minus ion concentration, and the pH is greater than 7. The pH of some common substances is shown here. The pH of a solution can be roughly estimated using a pH paper that gives different colors in solutions of different pH values. For accurate measurement, pH meters are used instead of pH papers. A pH meter is an electronic instrument that measures the pH-dependent electrical potential of the test solution. As we saw earlier, the ionic product of water at 298 Kelvin is equal to the product of the concentration of H plus and OH minus ions, which is equal to 1 multiplied by 10 to the power of -14. On taking negative logarithm on both the sides of the equation, we get negative log of Kw is equal to negative log of H plus and OH minus ion concentrations, which is equal to negative log of 1 multiplied by 10 to the power of -14. Negative log of H plus and OH minus ion concentrations can further be written as negative log H plus ion concentration and negative log of OH minus ion concentration. This is equal to negative log of 10 to the power of -14. As negative log of Kw is equal to pKw, negative log of H plus ion is equal to pH, and negative log of OH minus ion concentration is equal to pOH. Thus, the ionic product of water at 298 Kelvin, pKw, is equal to pH plus pOH, which is equal to 14. Based on the pKw value, the pH scale has markings from 1 to 14, and the nature of a solution as neutral, basic or acidic is determined depending on its value on this scale. The use of pH to indicate the strength of an acid or a base is limited as its value changes with the change in the concentration. As a result, chemists looked for a better alternative and found the dissociation constant to be a better tool than the pH scale to express the concentration of weak acids and bases. Consider the dissociation of weak acid HA in water to derive the expression for its dissociation constant. As we know, weak acids dissociate to a very limited extent in water. Equilibrium between the dissociated ions and undissociated molecules is established soon. This equilibrium can be expressed as HA aqueous plus H2O liquid in equilibrium with H3O plus aqueous and A minus aqueous. The equilibrium constant for this reaction can be written as Kc is equal to the product of concentration of H3O plus and A minus ions divided by the product of concentration of HA and H2O. As the concentration of water does not change, it can be taken as constant. Hence, it may be written as Kc into H2O is equal to the product of concentration of H3O plus and A minus ions divided by the concentration of HA. Since Kc and concentration of water both are constants, their product is also constant, and it can be taken as Ka, that is, Ka is dissociation constant of weak acid. As the dissociation constant is the equilibrium constant, it is affected only by a change in temperature and not by a change in concentration. Hence, the value of the dissociation constant provides the exact measure of the extent to which an acid is dissociated. In other words, the strength of the acid. The stronger the weak acid, the greater is the extent of dissociation. The greater are the concentration of H3O plus and A minus ions, and the larger is the value of Ka. The extent of the ionization of weak acids is usually expressed in terms of degree of ionization, which is denoted by alpha. Let us take the same generic example of the dissociation of weak acid, HA, in water to derive the expression for the degree of dissociation of weak acids in water. Let C moles per liter be the initial concentration of weak acid HA, and let alpha be its degree of dissociation. At equilibrium, the number of moles of the reactants will be C into 1 minus alpha, and that of the products at will be C alpha and C alpha respectively. The dissociation constant Ka for this dissociation equilibrium can be written as Ka is equal to the product of concentration of H3O plus and A minus ions divided by concentration of HA. Substituting the equilibrium concentrations in this equation, we get C alpha multiplied by C alpha divided by C multiplied by 1 minus alpha. Thus, Ka becomes equal to C alpha squared divided by 1 minus alpha. This expression helps us in calculating the degree of dissociation of weak acids when the dissociation constant is known. The values of Ka range from 0.66 to as low as 1 multiplied by 10 raised to the power minus 10 and even smaller. Hence, to accommodate such a wide range of values, the logarithmic scale is used. It is expressed as pKa equals negative log of Ka. The stronger the weak acid, the higher the value of Ka, and the lower is the value of pKa. For example, among the halogenated fatty acids, fluoroacetic acid with a higher value of Ka and lower value of pKa is the strongest. The dissociation constant Ka helps us in calculating the pH, equilibrium concentration, and degree of dissociation of a given weak acid. This problem will help you understand the steps to calculate the degree of ionization, equilibrium concentrations, and pH of a solution when the initial concentration and dissociation constant of the acid are known. The ionization constant of hydrocyanic acid is 4.9 multiplied by 10 raised to the power minus 10. calculate the degree of dissociation, the concentration of all the species, and the pH of a decinormal solution of hydrocyanic acid. The first step in solving this problem involves writing the equation for the ionization of a weak acid in water. The equation for the ionization of hydrocyanic acid in water is HCN aqueous plus H2O liquid in equilibrium with Cn minus aqueous plus H3O plus aqueous. In the second step, set up the ICE chart. The initial concentration of hydrocyanic acid is given as 0.1 m. The initial concentration of the products is 0. Since the reaction is yet to happen, the change in concentration on proceeding to equilibrium in terms of alpha is minus 0.1 alpha for hydrocyanic acid and plus 0.1 alpha and 0.1 alpha each for Cn minus and H3O plus ions. The equilibrium concentration of hydrocyanic acid is 0.1 multiplied by 1 minus alpha and 0.1 alpha each for cyanide and hydronium ions. In the third step, substitute the equilibrium concentrations into the equilibrium constant expression for the reaction and solve for alpha. The expression for the dissociation constant of hydrocyanic acid can be written as Ka equals product of concentrations of cyanide and hydronium ions divided by concentration of hydrocyanic acid. On substituting the equilibrium concentrations into this equation, we get 0.1 alpha multiplied by 0.1 alpha divided by 0.1 multiplied by 1 minus alpha. As hydrocyanic acid is a weak acid, it undergoes dissociation to a very little extent, and hence the value of alpha is very small. Thus, 1 minus alpha can be taken as 1. Thus, Ka becomes equal to 0.1 alpha square. As the value of Ka for hydrocyanic acid is given as 4.9 multiplied by 10 raised to the power minus 10, we can write 4.9 multiplied by 10 raised to the power minus 10 is equal to 0.1 alpha square. Now, this can be written as alpha square is equal to 4.9 multiplied by 10 raised to the power minus 10 divided by 0.1. This becomes equal to 49 multiplied by 10 raised to the power minus 10. Hence, alpha is equal to square root of 49 multiplied by 10 raised to the power minus 10. This is equal to 7 multiplied by 10 raised to the power minus 5. Thus, the degree of dissociation of decimolar hydrocyanic acid is equal to 7 multiplied by 10 raised to the power minus 5. In the fourth step, calculate the equilibrium concentrations of the species in the reaction. As alpha is known, the equilibrium concentrations can be easily calculated. Thus, the equilibrium concentration of cyanide ion, which is equal to the equilibrium concentration of hydronium ion, is equal to 0.1 alpha, can be written as 0.1 multiplied by 7 multiplied by 10 raised to the power minus 5. This is equal to 7 multiplied by 10 raised to the power minus 6. The equilibrium concentration of hydrocyanic acid is 0.1 multiplied by 1 minus alpha, can be written as 0.1 multiplied by 1 minus 7 multiplied by 10 raised to the power minus 5. This is equal to 3 multiplied by 10 raised to the power minus 6. Calculate the pH of the solution in the fifth step. The pH of the solution can be calculated using the relation pH is equal to negative log of H plus ion concentration. Substituting the value of H3O plus ion in the equation for pH, you get pH is equal to negative log of 7 multiplied by 10 raised to the power minus 6. This is equal to 6 minus log 7. Log 7 is 0.8451. Hence, the pH of the solution is equal to 6 minus 0.8451. This is equal to 5.1549. Thus, the pH of a decinormal solution of hydrocyanic acid is equal to 5.1549. The ionization constant of weak bases can also be expressed in a manner similar to that for weak acids. Consider the ionization of a weak base, BOH, in water. The equilibrium for this dissociation can be expressed as BOH aqueous in equilibrium with B plus aqueous and OH minus aqueous. The equilibrium constant for the ionization of a base is called base ionization constant and is represented by Kb. The Kb for this equilibrium can be expressed as Kb is equal to the product of concentration of B plus and OH minus ions divided by concentration of BOH. The degree of ionization for a weak base can also be derived in the same way as weak acids. Let C moles per liter be the initial concentration of weak base BOH, and let alpha be its degree of dissociation. At equilibrium, the number of moles of the reactants will be 1 minus alpha and of the products C alpha each. The dissociation constant Kb for this dissociation equilibrium can be written as Kb is equal to the product of concentration of OH minus and B plus ions divided by concentration of BOH. Substituting the equilibrium concentrations in this equation, we get C alpha multiplied by C alpha divided by C multiplied by 1 minus alpha. Thus, Kb is equal to C alpha square divided by 1 minus alpha. Analogous to Ka, Kb also helps us in finding the pH, equilibrium concentration, and degree of dissociation of weak bases. On extending the logarithmic scale to Kb, you can write pKb is equal to negative log Kb. The stronger the weak base, the higher the value of Kb, and the lower is the value of pKb. For example, among the alkyl amines, dimethylamine with a higher value of Kb and a lower value of pKb is the strongest base. You have learned that a weak acid is related to its conjugate base through the equilibrium constant expression Ka, and a base is related to its conjugate acid through the equilibrium constant expression Kb. As the conjugate acid-base pairs are related through the equilibrium constants, you can also assume that the equilibrium constants for an acid-base conjugate pair are also related to each other. Consider the dissociation of weak acid HA in water. The acid dissociation constant, Ka, for this equilibrium can be written as Ka is equal to the product of concentration of H3O plus and A minus ions divided by concentration of Ha. Ha, being a weak acid, has a strong conjugate base A minus. The dissociation equilibrium of strong conjugate base A minus in water can be represented as A minus aqueous plus H2O liquid in equilibrium with HA aqueous plus OH minus aqueous. The base dissociation constant, Kb, for the dissociation of this base can be written as the product of concentration of Ha and OH minus ion divided by A minus. On adding these two reactions together, the common terms cancel out, leaving the autoionization of water. The equilibrium constant for the net reaction may be expressed as K net is equal to the product of concentrations of H3O plus and OH minus divided by concentration of water raised to the power of 2. As the concentration of water remains almost constant, it can be ignored. Hence, K net is equal to product of the concentrations of H3O plus and OH minus ions. Recall that the product of H3O plus and OH minus ions is equal to Kw, the ionic product of water. Thus, K net is equal to the product of concentrations of H3O plus and OH minus, which is equal to Kw, the ionic product of water. Note that the equilibrium constant for the new reaction is the product of the equilibrium constants of the individual reactions. That is, the product of Ka and Kb is equal to the product of concentration of H3O plus and A minus divided by concentration of Ha multiplied by the product of concentration of Ha and OH minus divided by A minus. On cancelling the common terms, you get the product of concentration of H3O plus and OH minus. This, as you know, is equal to Kw, the ionic product of water. Hence, it can be concluded that the product of Ka and Kb is equal to the ionic product of water. This leads us to conclude that the equilibrium constant for a net reaction obtained after adding two or more reactions is equal to the product of the equilibrium constants for individual reactions. On applying the logarithmic scale to the equation, we get pKa plus pKb is equal to pKw, which is equal to 14. Some of the acids can donate more than one proton in their aqueous solution. Such acids are known as polyprotic acids or polybasic acids. For example, sulfuric acid and oxalic acid, which have two ionizable protons per molecule of the acid that can be donated, are called dibasic acids. Phosphoric acid, on the other hand, is called a triprotic acid as it can donate 3 protons. Consider the ionization of a dibasic acid, sulfurous acid, in water. Its ionization can be represented in the form of an equation as H2SO3 aqueous in equilibrium with H3O plus aqueous and HSO3 minus aqueous. The first acid dissociation constant, represented by Ka1, is equal to the product of concentration of H3O plus and HSO3 minus divided by concentration of H2SO3. Experimentally, its value is found to be 1.7 multiplied by 10 to the power of minus 2. Similarly, the ionization reaction of HSO3 minus can be represented as HSO3 minus aqueous in equilibrium with H3O plus and SO3 minus 2 aqueous. The second dissociation constant, represented by Ka2, is equal to the product of concentration of H3O plus and SO3 minus 2 divided by concentration of HSO3 minus. The experimental value for this dissociation is equal to 6.4 multiplied by 10 to the power of minus 8. Did you observe that Ka2 is smaller than Ka1? For any polyprotic acid, the first proton is lost easily, while the last proton can be removed with great difficulty. It can be seen that the second proton has to be removed from a negatively charged species. Due to the electrostatic forces, it becomes difficult to remove a positively charged proton from the negative ion. Hence, for a polyprotic acid, the higher order ionization constants are smaller than the lower order ionization constants. Have you ever wondered why some acids are strong and some are weak? The extent of the dissociation of an acid or the strength of an acid depends on the strength and polarity of the HA bond. In general, the weaker the HA bond, the less is the energy required to break the bond and the stronger is the acid. With an increase in the electronegativity of the atom directly attached to hydrogen, the charge separation between the atoms increases. This results in a weakening of the HA bond and an increase in acidity. For instance, the order of acidity of HF, H2O, NH3 and CH4 is HF greater than H2O greater than NH3 greater than CH4. The HF bond, because of its greater polarity, has less bond dissociation energy. This qualifies it to be stronger than the other given molecules. However, note that HF is a weaker acid than HI. Let's see why. Remember that while comparing the elements in the same group, the acidic strength increases with an increase in the size of the atom directly attached to the hydrogen atom. As the size of A increases down the group, the HA bond strength decreases, and hence the strength of the acid increases. Thus, the acidic strength of halogen acids decreases from Hi to Hf in the same order in which the size of the halogen atom decreases. Consider the dissociation of acetic acid in water. The equilibrium for this dissociation may be represented as CH3COOH aqueous in equilibrium with H plus aqueous plus CH3COO minus aqueous. Suppose you add a strong electrolyte such as HCl, which furnishes H plus ions to this equilibrium. What do you expect? Following Le Chatelier's principle, this equilibrium will be shifted to the left, suppressing the ionization of acetic acid. Similarly, if you add sodium acetate CH3COONA that furnishes CH3COO minus ions, the equilibrium also shifts to the left, suppressing the ionization of acetic acid. These are both illustrations of the common ion effect. The common ion effect may be defined as the shift in the position of an ionic equilibrium caused by the addition of a solute that provides an ion that is a part of the equilibrium. You will learn how to evaluate the pH of the solution when an electrolyte containing a common ion is added to a weak acid or base through a problem. Calculate the pH of the solution resulting from the addition of 0.1 mole of sodium acetate to 0.1 mole acetic acid solution. Ka for acetic acid is equal to 1.8 multiplied by 10 to the power minus 5. The dissociation equilibrium of acetic acid in water may be represented as CH3COOH aqueous in equilibrium with CH3COO minus aqueous plus H3O plus aqueous. To determine the equilibrium concentrations of the substances, set up an ICE table. Let X be the extent of ionization of acetic acid. The initial concentrations of CH3COOH, CH3COO minus and H3O plus are 0.1, 0.1 and 0 moles respectively. The change in concentration after the dissociation of acetic acid is equal to minus XM for acetic acid, plus XM for H3O plus ion and plus XM for acetate ion. The equilibrium concentrations of CH3COOH, H3O plus ion and CH3COO minus ions are 0.1 minus X moles and 0.1 plus X moles respectively. The equilibrium constant expression for this reaction can be represented as Ka is equal to the product of CH3COO minus and H3O plus divided by concentration of CH3COOH. Substituting the value of Ka and of the equilibrium concentrations of acetate, hydronium ions and acetic acid, we get 1.8 multiplied by 10 to the power of minus 5 is equal to X multiplied by 0.1 plus X divided by 0.1 minus X. as the acid dissociation constant Ka is small for a weak acid, the extent of ionization X can be assumed to be very, very small than 0.1 mole. Hence, you can assume that 0.1 plus X is nearly equal to 0.1 minus X, which is nearly equal to 0.1. Thus, 1.8 multiplied by 10 to the power minus 5 is equal to X multiplied by 0.1 divided by 0.1. This is equal to X, which is nothing but H plus or H3O plus ion concentration. Thus, the pH of the solution is equal to negative log of 1.8 multiplied by 10 to the power of minus 5, which is equal to 4.74. Salts are formed by the neutralization of an acid with a base, or vice versa. For example, when hydrochloric acid reacts with sodium hydroxide, sodium chloride and water are formed. Generally, salts undergo complete ionization when they dissolve in water. The cations or anions formed on ionization react with water. And produce weak acids or weak bases, or both. As a result, the pH of the solution is affected. The process in which cations or anions react with water to produce an acidic or alkaline solution is called salt hydrolysis. Hydrolysis is the reverse of neutralization. In hydrolysis, salt reacts with water to give a mixture of an acid and a base. For example, when sodium acetate is dissolved in water, it gives a mixture of acetic acid and sodium hydroxide. There are three types of hydrolysis. Hydrolysis of salts of weak acid and strong base. Hydrolysis of salts of weak base and strong acid. Hydrolysis of salts of weak base and weak acid. Let's study each type in detail. Sodium acetate is a salt of weak acetic acid and strong sodium hydroxide base. It undergoes complete ionization in water to give acetate ions and sodium ions. The acetate ion, being a strong conjugate base of a weak acid, undergoes hydrolysis in an aqueous solution to produce OH- ions. Hence, its solution is basic. That is, its pH lies above 7. Thus, it can be concluded that the aqueous solution of a salt of a weak acid and a strong base is alkaline due to the hydrolysis of the anion. Ammonium chloride is a salt of a weak base, ammonia, and a strong acid HCl. the NH4 plus ion, being the conjugate acid of a weak base, is stronger. When the salt is dissolved in water, the NH4 plus ions undergo hydrolysis to form NH4OH and H plus ions. Ammonium hydroxide is a weak base and hence remains almost unionized in a solution. As a result, the concentration of the H plus ions increases in the solution, and this makes the solution acidic. Thus, the pH of the solution is less than 7. Hence, the aqueous solution of a salt of a weak base and a strong acid is acidic due to the hydrolysis of its cation. Ammonium acetate is a salt of a weak acid, acetic acid, and a weak base, ammonia. As both the acid and the base are weak, their conjugates CH3COO- and NH4 plus ions are strong. Hence, both of them undergo hydrolysis in aqueous solution. As H plus and OH minus are produced, the solution is almost neutral. That is, the pH of the solution is nearly 7. Thus, the aqueous solution of a salt of a weak acid and a weak base is almost neutral due to the hydrolysis of both the anion and the cation. Sodium chloride is a salt of a strong acid HCl and a strong base sodium hydroxide. As both the acid and the base are strong, their conjugates Cl- and Na plus ions are weak. Hence, they simply get hydrated but do not undergo hydrolysis. Thus, the solution remains neutral. Hence, the aqueous solution of a salt of a strong acid and a strong base is neutral, as neither the anion nor the cation undergoes hydrolysis. Now, let's look at the term buffer solution. Suppose you add a drop of concentrated sulfuric acid or concentrated sodium hydroxide to a liter of water. Does the pH of the water change? Yes, it does. The addition of 1 drop of concentrated acid to 1 liter of water increases the H plus ion concentration and makes it appreciably acidic. Similarly, the addition of a drop of concentrated alkali increases the OH minus ion concentration and makes it basic. Now, add 1 or 2 drops of concentrated sulfuric acid or concentrated sodium hydroxide to a solution of a mixture of acetic acid and sodium acetate. Does the pH of this solution change? No, the pH does not change. So, there are some solutions to which a small amount of a strong acid or a strong base can be added without appreciably changing their pH value. Such solutions are called buffer solutions. Thus, a buffer solution is a solution that resists any change in its pH on dilution or on the addition of a small amount of a strong acid or a strong alkali. Buffer solutions, or simply buffers, play a vital role in chemical, biological, and biochemical systems. Buffers help maintain the life process by maintaining the pH in the body at a constant level. The pH of blood is about 7.4. The pH of normal urine averages about 6.0. Any deviation in their pH indicates malfunctioning in the body. We have learned in the previous classes that the maximum amount of the solute that dissolves in 100 ml of the solvent at a given temperature and pressure is called solubility. These 4 beakers contain 100 milliliters of water each. In each of the beakers, 3 grams of different salts, sodium chloride, lithium fluoride, magnesium chloride, and barium sulfate are dissolved and stirred. What do you expect to happen? You observe that the salt in the beakers containing the solutions of sodium chloride and magnesium chloride dissolve completely, while the other 2 beakers still contain large amount of undissolved salt. From this, we can conclude that all the salts are not soluble in water to the same extent. Salts like lithium fluoride or barium sulfate, which show little solubility in water, are commonly termed as sparingly soluble salts. Do you know why all the salts are not soluble to the same extent in water? Let us try to understand this. The ions in an ionic solid are held together by strong electrostatic forces of attraction. For its dissolution in the solvent, energy is required to overcome the attractive forces between the ions. This energy is called the lattice enthalpy. Let us once again recap the definition of lattice enthalpy that we have already learnt. The lattice enthalpy of an ionic solid is defined as the energy required to completely separate 1 mole of a solid ionic compound into its constituent ions. When such an ionic solid is dissolved in a solvent, certain amount of energy is released. The amount of energy released when 1 mole of a solid salt is dissolved in a solvent is called the solvation enthalpy. In other words, the energy released during ion-solvent interactions or in the process of solvation is called solvation enthalpy. A salt is soluble in a solvent only when the solvation enthalpy is higher than the lattice enthalpy of the salt. That is, the solubility of a salt depends on the amount of solvation enthalpy, which in turn depends on the nature of the solvent. For example, sodium chloride is highly soluble in polar solvent, water, because the solvation enthalpy of water is sufficiently high enough to overcome the lattice enthalpy of the sodium chloride salt. On the contrary, you can observe that sodium chloride does not dissolve in kerosene or benzene. Kerosene and benzene are non-polar solvents. Their solvation enthalpy is small and not sufficient enough to overcome the lattice enthalpy of the salt. Hence, salts do not dissolve in nonpolar solvents. We are familiar to the fact that each salt has its characteristic solubility at a given temperature. Depending on the extent of solubility, salts are classified into three categories. Salts with solubility greater than 0.1 moles per liter are considered to be soluble. Salts with solubility between 0.01 moles and 0.1 moles per liter are considered to be slightly soluble. And salts with solubility less than 0.01 moles per liter are considered to be sparingly soluble. Now let us discuss the solubility equilibria of sparingly soluble salts, such as silver chloride. Silver chloride is a sparingly soluble salt. When it is added to water, only a small amount of it goes into the solution, and a stage is reached at which the dissolved and undissolved silver chloride are at equilibrium. That is, a saturated solution of silver chloride is said to be formed. Thus, a dynamic equilibrium is set up between the undissolved solid and the ions in the saturated solution, which can be represented by the equation as shown here. The equilibrium constant for this equilibrium can be written as K equal to the product of concentrations of silver ion and chloride ion divided by the concentration of silver chloride. You have learned that the concentration of solids and liquids are not included in the expression for equilibrium constant because their concentrations will remain constant. As the concentration of silver chloride remains constant, the product of K and the concentration of silver chloride in the equation is represented by another constant called Ksp, which is the solubility product constant or simply the solubility product. Thus, the above equation deduces to Ksp equal to the product of concentration of silver ion and chloride ion respectively. The experimental value of Ksp for silver chloride at 298 Kelvin is equal to 1.8 multiplied by 10 to the power of minus 10. This means that in a saturated solution of silver chloride, the product of the concentration of silver ions and chloride ions is equal to the solubility product Ksp of silver chloride. The solubility product of a sparingly soluble salt at a given temperature may be defined as the product of the concentrations of its ions in the saturated solution, with the concentration terms of each ion raised to the power equal to the number of times the ion occurs in the equation representing the dissociation of the salt. Mathematically, we can write Ksp expressions using molar solubility, S, in place of individual ion concentrations. Note that molar solubility is the number of moles of the substance present in 1 liter of the solution. If we define S mole per liter as the molar solubility of silver chloride, then S moles of this salt dissolve in 1 liter of solution. In a saturated solution of pure silver chloride, the concentration of silver ions is equal to the concentration of chloride ions, which is equal to S mole per liter. Substituting S instead of concentrations in the expression for solubility product, gives Ksp is equal to S multiplied by S, which is equal to 1.8 into 10 to the power of minus 10. Thus, the molar solubility S is equal to square root of 1.8 multiplied by 10 to the power of minus 10. This is equal to 1.34 multiplied by 10 to the power of minus 5 moles per liter. Thus, the solubility of 1 mole of silver chloride in 1 liter of solution is equal to 1.34 multiplied by 10 to the power of minus 5. The expression for solubility product may be written as Ksp equal to the product of the concentrations of the ions involved in the equilibrium, each raised to the power of the coefficient in the equilibrium equation. For example, consider a generic salt of type AX2. The equilibrium reaction for this dissociation may be represented as AX2 in equilibrium with A plus 2 and 2X minus. The solubility product Ksp for the salt AX2 can be written as Ksp is equal to the product of concentration of A plus 2 and X minus raised to the power of 2. A salt may give 2 or more than 2 cations and anions when dissolved in water. For example, consider the salt calcium phosphate. When calcium phosphate is dissolved in water, it dissociates into 3 calcium ions and 2 phosphate ions. The solubility product Ksp of calcium phosphate is equal to the product of the concentration of Ca plus 2 raised to the power of 3 and the concentration of PO4 minus 3 raised to the power of 2. If S is the molar solubility of calcium phosphate, then the concentration of Ca plus 2 ions will be equal to 3S and the concentration of phosphate ions will be equal to 2S. Substituting the concentration of calcium and phosphate ions in the Ksp equation for calcium phosphate, we get the solubility product Ksp is equal to the product of 3S raised to the power of 3 and 2S raised to the power of 2. This is equal to 27S cube multiplied by 4S square. The product of this is equal to 108 multiplied by S raised to the power of 5. Thus, the solubility product of calcium phosphate is equal to 108 multiplied by S raised to the power of 5. If the solubility product Ksp of the salt is known, then the solubility of calcium phosphate is equal to 1.05 multiplied by 10 raised to the power of minus 5 mole per liter as shown. You have learned that in a saturated solution, if the concentration of any one of the ions is decreased, then, as per the Le Chatelier's principle, more salt dissolves and the equilibrium shifts towards the right till Ksp becomes equal to Qsp. On the other hand, if the concentration of any one of the ions is increased by adding an electrolyte, then the equilibrium shifts towards the left according to the Le Chatelier's principle till Ksp becomes equal to Qsp. The common ion effect is used for the complete precipitation of one of the ions as its sparingly soluble salt with a very low value of solubility product for gravimetric estimation. For example, silver ions are precipitated as silver chloride, barium ions as barium sulfate, and ferric ion as ferric chloride or ferric sulfate. The common ion effect is not only used in the quantitative analysis of compounds, but is also for their purification. For example, sodium chloride, along with impurities such as sodium sulfate and magnesium sulfate, is purified by applying this principle. When hydrogen chloride gas is passed through a saturated solution of sodium chloride, the precipitation of sodium chloride increases and dissociation of sodium chloride decreases due to the chloride ion, which acts as a common ion. Thus, the sodium chloride obtained is free from impurities. The solubility of salts of weak acids, like phosphates, increases with an increase in the concentration of H+ ions or a decrease in the pH. This happens because the anionic part of the salt reacts with H+ ions to form the salt, such that the equilibrium shifts towards the right side. This means that the solubility of the salt increases so as to make Ksp equal to Qsp. Now, let's derive a relation between the solubility and H+ ion concentration for a mixture of a weak acid and its salt. Let's take a mixture of weak acid HX and its salt MX. MX ionizes to give M+ ions and X- ions. Then Ksp is equal to the product of molar concentration of M+ ions and X- ions. HX ionizes to give H+ ions and X- ions. Then Ka is equal to product of molar concentrations of H+ and X- divided by HX concentration. On rearranging the equation, we get X- divided by HX equal to Ka divided by H+. Taking inverse of both the sides and adding 1, we get Hx divided by X- plus 1 is equal to H+ divided by Ka plus 1. This can be written as Hx plus X minus divided by X minus is equal to H plus Ka divided by Ka. Now, on taking inverse, we get X minus divided by X minus plus Hx is equal to Ka divided by Ka plus H plus is equal to F. At a given pH, if the solubility is taken as S, then Ksp is equal to the product of S and Fs. That is, equal to product of S square and F. Therefore, solubility is equal to square root of Ksp divided by F. On rearranging the equation, we get solubility S is equal to product of Ksp and H plus Ka divided by Ka whole to the power half. So we can conclude that solubility increases with a decrease in pH or an increase in H+ ion concentration.